It's great to see you, all of you again on this weekend, second Saturday, and having to see a very complete auditorium full with students is always exciting. Today again we have a very eminent guest here, and you can say he's a eminent scientist here. He works in he's an astronomer and a data scientist, and he works in Caltech in USA. Caltech is California Institute of Technology, which is in United States of America, and he is obviously he is an astronomer, and he's also a deputy director at Center for Data Driven Discovery. He has come up with you can see a very interesting and a very hot topic right now, which is about the AI and astronomy, how things can be are interlinked now. I welcome Dr. Ashish Mahabal on the stage. He is from Maharashtra and Nagpur, Maharashtra. And also you can see later on also you can ask questions in Marathi and in English also. I welcome Dr. Ashish on the stage.
Thank you. Good morning, everybody. I'm glad to be back here. As I said, I'm from Maharashtra. In fact, I did my PhD here at IUCAA and I'm adjunct faculty here. But my main time I spent at Caltech in California. And I don't know how many of you read the news or have been looking at it. But right now there are many fires raging in Pasadena, California. I guess from TV news and so Caltech is very close to that, and many of my friends have been affected by that. So my feelings go out to them right now. But let's go and talk about astronomy, AI, and the future. So one of the things in the future and AI that I'll bring about is how we should be cognizant about things happening around us as well, and how whatever we do on Earth is what is going to help us with astronomy and the future, etc. So we'll come to that. And again, as was mentioned, in the end, when we take questions, I'll be happy to take questions both in English and in Marathi, and I'll try to respond accordingly. So let's get started. Thank you for being here again. This is the broad outline overview of my talk. So what we'll do is that we'll talk about how astronomers do astronomy, or how that has been changing a little bit. Connection with space exploration, because that has been what has been happening a lot recently, and that's going to get more and more as we go along. And then in all of this, where does AI come in? Not just in astronomy and space exploration, but other walks of life which get connected to this. And so how that is very closely related to the future that we'll be living in, especially you will be living in, and the next generations will be living in, how that becomes very important. And then again, your responsibilities in connection with all of that. Again, if there are any specific questions in between too, what you could do if you want to just ask a question. I may not answer all the questions in the middle, but it's okay to ask questions, and we'll see how to go about that. Make it dynamical. Try to make it more interactive rather than just a long talk. So, what do astronomers do? What do you think how astronomy is done? How many people think that astronomers look through telescopes? Can you raise your hand? Okay, only a few people think astronomers look through telescopes, and how do they do? There are a few more hands, good. What about doing pointed observations? By pointed observations, what I mean is that decide where the telescope should be pointed, take your telescope and point it there, right? These are the two primary modes astronomy was done for a long time. So when the telescopes were small, you could look through the eyepiece, but as telescopes grew, what we really need to do is be able to collect the data. So why do you think there were very few hands raised? So, okay, let me reverse the question. Maybe that will be better. How many people think that astronomers do not look through telescopes? Raise your hand. There are a few more hands, and many people did not raise their hand for either of the question or the negative. Does it mean that the question did not reach them? Is it because it should be asked in Marathi? असं किती लोकांना वाटतं की टेलिस्कोप्स मधनं ॲस्ट्रॉनॉमर्स पाहून अभ्यास करतात? हात वर करा. किती लोकांना वाटतं, हात खाली करा, किती लोकांना वाटतं की टेलिस्कोप्स मधनं न पाहता ॲस्ट्रॉनॉमर्स त्यांचं काम करतात? Okay, अजून काही हात आले. Okay. So again, what we want to find out is we want to get more details, and as the telescopes grow, the size is big, so they are collecting a large number of photons. And the important thing to remember, when you look through your eye, no matter how big the telescope is, there is one fundamental limitation that comes in. You would have seen on a TV screen how the picture gets updated, right? So there is something called persistence of vision. How many of you have heard of persistence of vision? So persistence of vision tells us that our eye can respond to 1/25th of a second of the light, and then it gets refreshed, right? So even if you are looking at the sky through a large telescope with your eye, the data that your eye can collect can last only 1/25th of a second, and it gets refreshed. So you cannot really keep on collecting that, and that is why what is important to have a camera at the back of the telescope, and that way you can keep the aperture of the telescope open for a long time. So for instance, some of the surveys that we do, and I will come to what surveys mean. What we have is we can keep the telescope open for 30 seconds, or there are some other telescopes with small fields of view where we can keep it open for 30 minutes. Now with our eye, that wouldn't have been possible, right? Even if you keep your eye open for a long time, it is not collecting data all the time. It's collecting data all the time, but only for those small fractions that you have. So it is not adding up the data, which is what is important to be able to see faint. So for instance, you know that our eyes have rods and cones. So when you go in the dark, they get adjusted and you can start seeing fainter things. Or when you enter a dark room, you may not immediately see anything because your eyes were adjusted to outside, but then slowly you can see things. So there is some chemistry happening in the eye that has been changing that. But with telescopes and physical devices, what we do is that we have cameras at the end. So long back, there used to be point and shoot cameras, there used to be photographic film which you had to develop, etc. But right now, many of you have smartphones. So how many of you use phones with cameras? Right? Many of you do. And so those cameras are much better. So those also, there are some of them have night mode, or some of those have longer exposures. So those are the ones that can collect more data, and that is why you can we can take images of darker parts also. So that's exactly what astronomers do when they are taking images of the sky, right? And pointed observations is what used to be done for a long time. The way science used to be done is that you would think of a problem, you would think of a hypothesis. It could be very silly, or it could be complicated, or whatever. But then when you make a hypothesis, you need to collect data to support it. And to collect that data to support, then you would decide where should we be observing to figure out what the answer should be. So a simple thing could be, during some nights during the year, you can see the Milky Way. How many of you have seen the Milky Way? Some of you have. So it is, you should be able to go to a darker part of the sky and be able to see that. Even in Pune, there are some amateur astronomy organizations, so you could get connected with them, and where they do things like that, meteor showers, Milky Way, etc. observations. So there, suppose you wanted to figure out how broad the Milky Way is, as seen from Earth, meaning not in physical things. And so what you can do is that you can devise an experiment for that. So you can see what is the extent of the Milky Way and use some kind of a measure to see how broad that is and do some mapping. So that's the kind of hypothesis that I mean. So someone could say that the Milky Way size is 10 degrees. So we measure many quote-unquote distances in degrees, because that's one of the best measure to do, because the angles are being subtended. So one of the questions that I like to ask audiences like these is, we live on Earth, the moon goes around us, and the Earth goes around the sun with the moon. Which is bigger, the moon or the sun? How many think that the sun is bigger? Raise your hand. Okay. How many think that the moon is bigger? Raise your hand. How many think that they are the same size? Raise your hand. Okay, there are a couple of people who are raising their hand. So, can you try to say why you think they are the same size? I don't hear an answer. Okay, the question can be a tricky question, right? So how you are asking, if it is physical distance, then clearly the sun is much bigger than the earth and the moon is much smaller than the earth. But there is another thing called the angular distance. The angle those bodies subtend on our eyes. When you look in the sky, what looks bigger, the sun or the moon? Who think the sun looks bigger in the sky? Raise your hand. Okay, a few. Who think the moon looks bigger in the sky? Okay, there are more hands now, and that's Possibly because you can see more directly at the moon, and when the moon rises and it's full moon, you are seeing it at low horizon, so you are seeing it through a large amount of atmosphere, so it looks bigger because of that. How many think they look the same size? There are a few hands still. So we have total solar eclipses and total lunar eclipses, right? That should tell us that both of them are at least roughly the same size. I won't say exactly the same size, because how is the moon closer to Earth in a particular time of the year, or is the Earth closer to the sun at a particular time of the year changes those perceptions also. But angle wise, they're roughly the same size, and the size is half a degree, right? So this angle, how many degrees is this? 90, good, right? And so you can say this would be 60, this would be 30, and you can use that to see how tiny half a degree is. So someone could make a hypothesis about how big the Milky Way is. One could say that maybe it's 10 degree, and then someone could say that it starts at 5 degrees, become 10 degree and 5 degree. And so you can measure that, go out and measure that. So that is how science works, that is how physics works. So every proposition, every hypothesis that is there should be testable. There should be observations that you can take and then determine whether that works or not, right? And so in astronomy, one problem is that we cannot bring stars to the laboratory. We cannot try to increase the mass of a star or increase the size of a star and see how it behaves, right? And so we have to do observations that are far off, to collect those observations. And using these surveys over large amounts of time, we can try to do various things. So in the past, this is how things used to be done mostly, that you create a hypothesis, you have a hypothesis. You say, for instance, blue stars are hotter than red stars. Or someone could say red stars are hotter than blue stars. But then you have to figure out a way how you can measure that. So the way to measure temperatures of stars could be that you take a spectrum of the star, you compare it with, say, black body radiation of some kind, but you have to devise an experiment. And even if you cannot bring a star here, because you can take a spectrum and compare it to the laboratory spectrum and other things, you can then start determining things. Or how do you determine distances to stars, for instance? They are so far off. So there are certain methods to do that. You can figure out that certain kinds of stars have roughly the same brightness, and if they have the same brightness, then how they seem from here. So when I say they have the same brightness, I mean intrinsic brightness. Brightness as internal to the object, but when an object moves away from us, a lit object moves away from us, it looks fainter and fainter, right? So if there are two stars that are identical to each other, but they are at different distances, the brightness will look different. So using such information, you can figure out what is the actual brightness. Not all kinds of stars are like that. So there are some stars, say, called RR Lyrae stars. Not all RR Lyrae stars become the same brightness even intrinsically, but there are certain other stars that will become that. So for instance, you would use that, or there are certain kinds of supernovae that reach the maximum brightness which is the same. Supernovae type 1a. So those are the ones that you can use as what are called standard candles. So these are hypotheses. You make hypotheses, take specific observations, and then be able to answer those questions. But what has been happening is that science has been changing, astronomy has been changing. So we have been doing more surveys. It's not that we don't do pointed observations, but more science is getting done through surveys. And what a survey is where you look at a large part of the sky, you collect a lot of data. You do have questions in mind. You are going to use the survey to ask specific questions in mind, but also now using the data, you can let it drive new curiosity. You can say, okay, this is what data I have. What are more questions that I can ask of the data? So sometimes you can come up with questions that you did not have before and see whether you can get answers for it through the data. So this is what is changing because of big data. You may have heard the word big data. Even in the rest of the world, there is a lot of big data that is being collected on humans, in space, about Earth, and so on. That is what is helping us do many things. So for instance, these days, something like hurricanes, we get information about them much earlier. And that is because we have been studying atmosphere. We meaning not astronomers in particular, but data scientists and atmospheric scientists, climate scientists. So you get a lot of data about those. And then you can make models, you can make predictions about those. So all those big data can drive things to faster computers, GPUs, internet, and so on. And now, at your fingertips, because of the internet, you can learn so many more things. So you need to be curious, you need to be asking questions related to that. So surveys, there are many kinds. You know of electromagnetic spectrum. So we have infrared, we have visible, we have ultraviolet, but even beyond that, you have got X-rays and radio waves, and so on. So all of those are electromagnetic waves, and you can have telescopes for all of that. GMRT, for instance, which is run by NCRA, which is next door to IUCAA, it's a radio telescope. It's a large and fantastic radio telescope. So the radio waves that are coming from the sky, from different galaxies, from some stars, etc., those are detected by that telescope, and you get information about that. Optical astronomers use optical telescopes, which is what is most people are familiar with. But there are also X-ray telescopes. There are also infrared telescopes. There is going to be the Roman telescope that will be launched next year, for instance, which will be collecting a lot of information in infrared from the sky. You know of Hubble Space Telescope, which is an optical telescope. There's another optical telescope that was launched just a few years back. What is its name? James Webb Space Telescope, correct. It's bigger than Hubble Space Telescope, but both these are optical. So Roman telescope is going to be more in the infrared, so we'll get different kind of information about stars and galaxies and other kinds of objects. And for a long time, electromagnetic radiation was the only way we could get information from the rest of the universe about different kinds of objects. But only in the last few years, there are two new windows that have opened up on the universe, which are not electromagnetic. One is, and I have listed them both here. So, gravitational waves is one and neutrinos is another. So, how many of you have heard of gravitational waves? Okay, some of you have. You know that there is a new gravitational wave detector being built in India. Not just in India, but in Maharashtra, near Hingoli. So, that will be the third LIGO detector that will be built. There are two right now in the US, and there are a couple of other gravitational wave detectors. So gravitational waves are very interesting. What happens there is that when two black holes merge or two neutron stars merge, there is a gravitational wave that gets sent out. There are smaller gravitational waves that are sent out even through smaller collisions, but that are really tiny. Even the black hole collision gravitational waves are really small, but we have managed to build detectors that are very sensitive. So these LIGO detectors, for instance, are L-shaped detectors. Each arm is about 4 kilometers. And then, how many of you have heard of interference of light? So when you have light beams, they can be out of phase or in phase, and then depending on that, how the wave nature of light determines what are you going to see. So in these LIGO detectors, what happens is that when a gravitational wave comes, the shape of the two arms can change because of that. And there is interference happening inside of those detectors that can go out of whack, that can be broken because of such a wave, and that is what is being detected. Really, really sensitive things. And then neutrinos are passing through all of us all the time, but then we now have a detector which is 1 kilometer by 1 kilometer by 1 kilometer near Antarctica. It's an ice cube. So that is being used as for neutrino detection, so we can see how neutrinos come about. So there are these all kinds of surveys. That is the main thing that I wanted to say. And so let's right now look at only some of the optical surveys. And so let me focus on these things. So CRTS is a survey that I worked on long back, Catalina Real-Time Transient Survey. This was mainly to look for asteroids because we would take 4 images in quick succession, and in the first 3 images, asteroids, we'll see them moving, then we'll predict where it should be in the 4th image and confirm that it is indeed there. So that is how we can confirm that it is indeed an asteroid. ZTF is the survey that I am currently working on. Zwicky Transient Facility, this also covers the northern sky. Every 2 to 3 nights, we get the entire sky. So let me give you an example as to how astronomy had changed. 25 years ago, when I first went to Caltech, I was working on another survey which had just been completed. It had taken 15 years to collect 3 terabytes of data. 15 years for 3 terabytes. 25 years ago, that was huge, that was big, right? But now with this ZTF, which is operated from the same telescope, we collect 3 terabytes every 2 nights. So what used to take 15 years before can be done in 2 nights and better quality than that, right? So that is how things have been changing, and you should be able to take advantage of many of these data sets because many of these data sets are publicly available. So if you know a little bit of programming, you can download some of these data sets, ask probing questions and do that. And there is huge scope to do lots of things, and this is intended more for the teachers in the audience, that astronomers are so few and the data are getting so big that most astronomers still go after low-hanging fruit. And in the data sets that are available out there, there is a lot that can be done even by students who are a little curious, know a little bit of programming, etc., if they get onto it quite early. So that's really useful. Gaia is another telescope which is in the sky. It's more for astrometry. What it's doing is that it's trying to map our galaxy at extreme precision, positional precision. When you have a telescope on Earth, one disadvantage is that the light comes through the atmosphere. What that means is that there is simmering that happens and star seems to twinkle. Whereas if you have a telescope outside the atmosphere, then no such thing happens and you can measure the positions more precisely. So planets, the word comes because they are wanderers. The background of stars seem fixed, whereas planets have a little bit of motion because they are going around the sun. But even stars have motions, right? Because within the galaxy, even stars are moving. And those movements, how the streams of stars are, can be helped understood by telescopes like Gaia. Because we need to understand the dynamics of our galaxy. So those are the kinds of things that get done with that. And Rubin LSST is a large telescope in the southern hemisphere. So ZTF is in the northern hemisphere. We can look at the northern sky, whereas what Rubin would do is that it will look at the southern hemisphere more. It's a very large telescope, 8-meter telescope. ZTF is 1.2-meter telescope, so you can see how big it is. And its effective area is 6.7 meters because there is a hole in the middle from where we put instruments, collect the data. But 6.7 compared to 1.2 is still 5.5 times bigger, and that's in one dimension. And because collecting area is square, circle is a r square, right? And so 5.5 multiplied by 5.5, which is about 3,000 times more. So LSST Rubin telescope will be able to collect 3,000 times more photons in a single image compared to say ZTF. So it can see much more fainter. So that has already taken first light. The observations are starting up, and so over the next 10 years, it's going to provide us with very deep images of lots and lots of things. There are many other telescopes, many other surveys happening. We can't go into all of these, but these are various things that are important. How big the telescope is. So telescope being big, the mirror being big is one thing, but how big its field of view is also matters, important thing. So that's the field of view. Cadence is how frequently the observations happen, what kind of filters are used, because we cannot cover the entire electromagnetic spectrum at the same time if we want to understand properties of the stars like temperature, right? And so that is why we have different filters like RGB. We divide the electromagnetic spectrum into small parts. What is the total area of the sky that the survey covers? How long the survey stays on, etc. So what is the temporal resolution? How many seconds it observes, etc. All these are important questions which get used to determine what. And that is why there are many surveys which complement each other, so we know more and more about different things, right? And so what is it that astronomers look at? We look at solar system objects. It includes the sun. Observing the sun itself is important. A mission that India launched towards the sun. Who can say its name? Yeah, great, Aditya, right? And then there are so many planets in our solar system, so we are studying those. There is one planet towards which India sent a mission some time back. Which planet? Mars, Mangalyaan, right? And then there are asteroids. Do you know that humans have managed to land on asteroids? Not a human being, but humans have managed to land instruments on asteroids. Did you know that? Okay, many of you are saying yes, so we'll take a little bit of information, look at that a little bit later on. And then there are also comets, right? Fantastic things. There was one comet visible last year. How many of you saw that? Very few. Okay, so when comets come, they're fantastic things. So try to make way to outside the city to look at it sometime. In stars, there are many types. Again, there are binary stars, two stars going around each other, white dwarfs or supernovae that are stars that die, etc. Or we also study galaxies, different kinds. There are spiral galaxies, elliptical galaxies, clusters of galaxies, etc. Cosmology involves studying the universe itself, how the evolution has been happening. So using, say, supernovae or distant galaxies, etc. And then exoplanets, that has become fairly hot recently. How many of you know what exoplanets are? Raise your hand. So these are planets being found moving around, going around other stars far away from us. So planets not in our solar system. And there are several thousand that have been found. There was a Kepler mission earlier, there is a TESS mission going on right now which is finding these. So it's important for us to understand that we know that life exists on Earth, right? Yes? Okay, is it intelligent life? We don't know, right? So, what we'd like to see is there is life on other exoplanets, on exoplanets in general, and then what level it would be. But for that, we need to understand the properties of planets themselves. So, is it by accident that planets formed in the solar system, or is it common that planets form all the time around stars? So, we've been finding more and more planets. And there have been very interesting kinds of planets that have been found. Some very small, some much larger, and so on, right? And so, that's something that's going to get bigger and bigger as we understand the atmospheres of these temperatures, what are the properties that are required for life to stay on these, and so on. And so, how is this connected with space exploration? Because these observations, when you use telescopes, you look at various things from the Earth or from telescopes that are in the sky, but what about space exploration? Because many people, especially students, children, get interested in astronomy not so much because of these tiny little things about stars or something about galaxies and so on, but about space, right? Going into space, going to other planets and so on. So traveling to other planets seem exciting. So that's one of the reasons why many students early on learn about the solar system, what are the properties of the planets, etc. So in our solar system. But what about traveling to exoplanets? Can we go to some other planets? How distant are stars from each other? That distance is foreboding right now. I don't think we can go there very soon, but we should be thinking about how to do that anyway, right? And where have we gone so far? So if that is one of the interests, then let's look at space exploration a little bit. So these are some of the missions from the non-Indian missions like OSIRIS-REx, Hayabusa 2, DART, Europa, and there has been an interesting development in reusable rockets recently, which will help accelerate some of the launches, etc. But India also has a large number of missions. So AstroSat is a telescope that has been taking a lot of data about transients and X-rays, etc. Aditya, you already mentioned. Chandrayaan, we didn't say, but this Chandrayaan, Mangalyaan. Then, how many of you have heard of SpaceX? That was a very recent launch from India, just about 10 days back or so. And then there's going to be Gaganyaan later on as well. And so let's look at some of these missions. Is OSIRIS-REx, that is the one that collected material from an asteroid called Bennu. So this is how that asteroid looks. So many asteroids don't look round like planets do. They have broken things from a past planet, and then they have been drifting around, and various things have been happening to them. And this is how the launch itself happened. It took a long time for us to get there because we didn't just want to get to the asteroid. And these numbers show that. So we launched it in 2016 and got there in 2018. But then it took some time getting close to it, adjusting itself, because we didn't just want to go close by, take photographs and just whiz away, but we wanted to match the velocity with the asteroid so that when we try to land on it, we don't miss it, we don't just collide on it and break whatever we had sent there. So it had to be done very slowly. We matched the orbit correctly and then it got there and slowly landed there. Then there was we took out some material, the lid opened, the material was collected, it was closed, and then it slowly moved back. And then before moving completely towards Earth, it still stayed there a little bit to make sure that it had collected information and the data. Otherwise, it would have been required to go back and collect it. And once that happened, then it came back. And only in 2023, which was just over 1 year back, that it reached back to Earth. And now scientists are looking at all the material that have come from it. So, but the important thing is, now humans can reach things like Mars, Moon, and also asteroids, collect material from there, bring them back. And so a lot of things that you see around in community about planets directly ruling your life, affecting your life, that all doesn't have any, that doesn't hold any water. So if someone tells you that you have Mars in your kundali, so this is going to happen, no, that's not going to happen. These are planets, these are physical bodies. We understand them much better now. This is now how it was 100 years ago. Jupiter, Mars, and so on, those don't affect your lives directly. They will affect your lives if you're interested in them, in the sense that you can go there, maybe study them and so on, but only to that effect. There are other asteroids from where we have collected material before. So these were two Japanese missions, for instance. Hayabusa 2 on an asteroid called Ryugu. It was done from 2014 to 2018, and even before that, there was the which went from 2003 to 2010, another one. So again, there are many instances where this is happening. How many of you heard of this experiment DART? Again, a few of you. So these have been published in many different areas. So what DART was double asteroid redirection test. CRTS is a survey that I mentioned earlier where we were looking for asteroids. The reason we were looking for asteroids is because we are interested in finding out if there are any asteroids that may be bigger than 1 meter in size which could impact the Earth. Long back, as you know, 65 million years ago, very likely the dinosaurs were killed off by an explosion that happened because of asteroids, right? A lot of dust went into the atmosphere, etc. We don't want that to happen again. We don't want to get killed off. But if an asteroid does come our way, what is it that we can do? So we wanted to see, are there things that we can be doing and how controlled those could be? So this was a pair of asteroids, one asteroid and another asteroid going around that. And we decided that we'll go and hit the smaller asteroid and see how much its orbit changes against the bigger asteroid. There are two theories as to how asteroids are made. They can be solid balls or they can be made of rubble. Why can asteroids be made of rubble? Rubble in the sense that a number of pieces just sticking together loosely, not really like a solid thing. So think of the following situation, right? There is a space station and something happens to the antenna of the space station. So an astronaut who's on the space station goes for a spacewalk in a spacesuit, and the astronaut is carrying a spanner to set the antenna right. But then somehow the spanner goes out of his hand. It starts up. So what will happen to the spanner? Louder. It will float. But what does it will float mean? Because inside the space station it's zero gravity. Is it zero gravity everywhere? What happens? So it will start coming towards the space station because that is the biggest gravity that it has. Meaning, depending on at what velocity it was thrown or what velocity it was fell off, it will be less or more, but it won't leave the space station in general. It won't have escape velocity in general unless you use it to really launch it in some way. But so it will come around and be near, right? So similarly, if there are many particles and there is no big body nearby, those particles are going to stick around with each other because of each other's gravity. So that is what a rubble pool is. So we wanted to find out how much of these are rubble balls and how much are solid. And we knew that it's likely to be in between. So we had already models that if it is a solid ball, then this is how much the orbit should change. If it is a rubble ball, this is how much it should change. And as expected, it was somewhat in between the two. Why are we doing this? Because if an asteroid comes towards us, then can we launch something to deflect its orbit just enough so that we won't be affected? This did lead to a lot of debris, and that danger is always there because if we do this collision close to Earth, then a lot of debris could fall on Earth as well. So we have to be mindful of that. And this just sizes shown here for comparison of the two asteroids. This was the smaller asteroid size and this is the bigger asteroid size. And this is slightly bigger than the Statue of Liberty but smaller than pyramids, whereas this is bigger than Eiffel Tower but smaller than the tallest building that we currently have, right? So those are the sizes we are talking about. But the sensors that we want to do as astronomers is all the sizes that we can get to. In the physics department here, there is an interesting graphic which shows the various launches that have been done by India. So two different things around Aryabhat to Gaganyaan. And SpaceX is the satellite that was launched by India recently, where what they want to do is that these are two satellites in space, they want to bring them together. This docking capability, so far only 3 nations have, America, Russia and China, and India wants to be the fourth. The 1 or 2 of the first experiments didn't work as well. The telescope are still, the satellites are still away, but we are going to try again to bring them together and see how that works. So, astronomy and being astronauts are not the only 2 things that you can do if you are interested in astronomy. There are so many other things that you can do. You can get into teaching of astronomy. You can get into communicating of astronomy. So, difficult concepts, how you can communicate as a reporter or through newspapers and magazines and so on to different people, that is an important thing. You can build instruments, right? So it doesn't have to be that you have to look through a telescope or become an astronaut. You can build an observing instrument if that's the kind of thing that you're interested in. But you could also be civil engineers, how to design observatories. What are the properties that are needed for an observatory? You can study those, you can help with those and so on. So no matter what you are interested in doing, there are ways you can stay connected with astronomy. So if you're interested in astronomy, you should follow some of those paths. But there are two other things that I'm going to mention that you can become. You can become a citizen scientist, where even if you're not doing a big project, for the existing projects, how you can contribute to that. And one more thing that you can do is you can become a skeptic. Becoming a skeptic is very important, asking questions of others, of yourself, because that is how you can grow, that is how your curiosity can continue. And so we'll see a few things related to those two now, the last few minutes. So this is what brings me to AI. Right now, one of the big AI things that is happening is the large language models or something like ChatGPT. So how many of you have used ChatGPT? Okay, many of you. Those of you who have not used it, especially the teachers, I would urge please use it as soon as possible, right? Because you should understand what are the benefits of it, you should understand what are the dangers of it. And there are many, many hallucinations that can happen and we need to be aware of that. Even if these are large language models, right? I mean, they're not necessarily the best models yet. They are getting better and better, and one day they will surpass us, but that day we are not sure how close or far away that is. But that's something that's quite important to know about. So, they have brought about a big change, right? You can ask so many questions. Many people have stopped using Google, for instance, and are using these. These are primarily saying what the next word is. So these models, the way they work is that they're saying what the next word is, then what the next word is, what the next word is. And if the model is created well, if a big corpus has been used, then it is better at doing that. So for instance, how does this work? If I say I, right, in an English sentence, what is the next word that I can say? Or will, or was, or there are many such things, right? And now if I give you a book, and in that book you figure out all possible sentences which start with I, and then there is something as a second word, you say how many times was appeared, how many times am appeared, how many times will appeared, how many times may appeared. So you make a list of that. And then that will tell you the frequency of each of those words, which appears more times. So the one that appears, suppose was appears 100 times, may and everything else appears 555 times. Then if you want to blindly guess what will be the next word, then was is most likely the word, right? In some cases it may be wrong, but in most cases it will be correct. So that is the simple principle that is used, but of course much more complicated. Because there are many sentences, many nuances. The next thing that happens is that there is a hyperparameter called temperature. If the temperature is set to 0, then it gives you the most probable word. But if the temperature is set to higher and higher, even to 1, then it becomes more creative. And it tries to experiment with this and that. And it says, okay, let me try this because it may go better with that, and so on, those kinds of things. And that is why it can become more creative and give other things. But they can hallucinate. They can also give you answers that are not right. And so there are many types of hallucinations. There can be factual inaccuracies. It can say 2 plus 2 is 5, for instance, in some cases, because it doesn't understand numbers, right? It understands nothing, by the way. It is just a model. Or it can give speculative assertions that how many seconds would I survive on the moon if you ask it? If it doesn't know, if no one has any data on it, it could just speculatively give that. So my favorite example of all of these is that in early days, some of these models, one of these models was asked, does Australia exist? Does it exist? Okay, most of you are saying yes, good. So, but very few people explicitly write that Australia exists. Very few articles you will find a statement that Australia exists. Why would you make such a statement? Everyone knows it exists, right? But there are some people, conspiracy theorists, who say Australia doesn't exist, mostly from North Hemisphere, right? They say, oh, that's just something that someone made up. Yeah, there are people of that kind, I know, right? So, when you look at a corpus of data, when these large language models collected these data randomly, they found sentences that said Australia does not exist, and they didn't find sentences that say Australia exists. And when you ask whether Australia exists, they would say Australia does not exist, because that had a higher weight. So you have to be aware of those things. This was an obvious example, but there are many subtle examples. There's a lot of misinformation that is spread out there through LLMs, so you have to be wary. And the way to do that is to question LLMs, but not just question these large language models, but you should learn to question everything you are being told, no matter who tells them. Because using logic and using scientific techniques, scientific principle, you should be able to answer most questions yourself. And for that, what is critical is thinking, being curious, asking those questions. Especially today, that has become really important, even in science, because even in science, what many people have started doing, especially students, doing their homework, trying to go to something like ChatGPT, that is not a good idea, because unless you understand things, unless your fundamentals are good, that's not going to help you. You can use ChatGPT to look at some of the things, speculative things, asks to fill in some of the gaps, but again, understanding all of that is very, very important. So, your responsibilities are about thinking, you should think, and you should learn. Don't get spoon-fed from large language models or from elders or from phones. Don't believe things that you see. Learn to question them and keep on doing them. That is what the recipe will be for building a great humanity in general and becoming good citizens, becoming good humans. So let me now come towards the citizen science aspect where some of these things come together. So the LLMs are generative kind of AI, especially text generation. What is the next word? What is the next word? But there are other kinds of AI that are there which are generative and non-generative. So among generative AI, there are these image making models, right? When you give a prompt, they can create images for you. There is also a model that gives you videos, Sora, that was released recently. If you give it a prompt and say make a video of. So this is another example that I like to give. So suppose some of you are in cooking and you ask how do I cook, say brinjals, right? And you ask ChatGPT. ChatGPT can give you a recipe of that. Now you can feed this recipe into another model and say now make a video of this. So it can make a video of someone cooking brinjals, right? It has become that easy. There will be hallucinations in that, there will be mistakes in that. So we were at an astronomy and AI conference this last week, and a comparative image were shown of two people in a cafe in Bangalore and two people in a cafe in Pune. And you couldn't say what is the Pune-ness in the Pune image and what was the Bangalore-ness in the Bangalore image, right? So they are more generic. They pick up some elements but not really the nuances. And our neural networks are much better at picking up the nuances because we have the background. We have been growing up steeped into visual things. The large language models, they are looking at only the text, whereas we are looking at various visual inputs also. So what astronomers do besides generative is a lot of classification, understanding the data through machine learning. And that is not completely generative, that is well understood, a lot of things. There also we need to break in more explainability, but we are getting there more and more. So this is a tree of various types. I mentioned stars and galaxies, but even when you look at stars, there are stars of one kind, stars of second kind, and within that there are subtypes, etc. So there is extrinsic variability and intrinsic variability. Intrinsic variability is when something happens inside the body. A solar flare, right? You would have heard of all these things that were happening some time back, northern lights. So at that time, why that happened is that energetic particles from the sun were ejected. We are near the solar maximum. They interacted with the atmosphere of the earth, and that is what gave rise to that. So those changes are intrinsic to the sun. But if there are two stars going around each other and one eclipses the other, then that is like extrinsic variability. It seems that one of them is becoming fainter or brighter, but it's not really becoming fainter or brighter. It seems from us. But even that is important for us to understand the properties of those objects. And then even within the extrinsic variability, there is microlensing, eclipsing, rotation. So for instance, when the sun has a lot of sunspots, if you have a very sensitive instrument, you can see that the brightness goes down a little bit. Or if there is a flare, then the brightness goes up a little bit. So those kinds of things that we can do. And Zwicky transient facility that I mentioned earlier, we have a survey where we have got thousands of observations of every object in the northern sky. And 1 billion objects, right? So what's the population of Earth? Roughly 1 billion, a little bit more than that. And we have that many objects that we have observed. So that is where humans are not really sufficient to do observations, to do analysis of all these objects. And that is where we need machine learning. And that's where we have been using AI in many different ways. So what we do when we find interesting objects, we create what are called alert packets. So we have a reference image from before where we have combined past images. So it's a deep image. And then in the latest image, if you find something that was not in the deep image, that's interesting. So what that means is that for a long time we were looking at a part of the sky, we saw nothing at a given location, but suddenly now there is something. So this, for instance, is a star that was there in the reference image and it is also there in the science image. But look at this small faint thing that is next to it, right? In the reference image it was not there. So in the 30 seconds we saw something come up. What that means is that it could be a supernova, it could be a bright variable which was below our detection limit before, but we'd like to know more. And that is why we release these packets, including the time series. So this is a few days here, so it was not detectable for several days, but then suddenly it was detected, not only detected, but becoming brighter. So this is brighter, this is fainter, and this is magnitude scale. Every magnitude is 2.5 times brighter than the bigger magnitude. So with the naked eye, you can see objects from 0th magnitude, which are roughly brightest, as seen by the naked eye, and 5 magnitude is the faintest, that's 100 times. So this 2 is roughly 2.5 times, so this is 6.5 times brighter than here. So that object became 6.5 times brighter than before in a few days. And we can find those. And then we release these alerts, anyone can access those, other telescopes can access those, so they can use a different filter to observe them, etc. So what we have done is that we have developed a game called ZART with this. This is ZTF Augmentative Reality Transient Hunter, and every night we put fresh discoveries in this app so that you can start playing around with that as well. And it's available both on iPhones and on Androids, and that will tell you newer and newer things. Again, if there are teachers who are interested in doing some STEM activities with this, then we can talk more, because you can bring these in specific ways. So we got interested in this like Pokemon, so it's like Pokemon Go but for astronomy. Maybe some of you have played Pokemon Go. How many of you have played Pokemon Go? Okay, a lot of you. So then Pokemon are of different types. What we did is that we said there are variables and transients of different types. Why not do the same thing? In for Pokemon Go, you go around the earth looking for them. Here you can point your phone to the sky and look for transients and find them. So that is what we did. And some undergraduate students, so who are only a few years older than you, developed this game for us. And so many of these were from India, IIT Mandi, IIT Gandhinagar, etc. And this is how the main screen of ZARC looks. And we have primarily 4 kinds of objects that are hosted. So an object, a transient that is in a galaxy, or a nuclear, which is not just in the galaxy but close to the center of the galaxy. So it could be an AGN, an active galactic nucleus, or a tidal disruption event where a star is just ripped apart by the central black hole in the galaxy, or it could be a supernova that is close to the center. Or there are variable stars which are persistent but go up and down in brightness. Or orphan objects where there was nothing there before but it has suddenly become brighter. And we also have 2 types which are what we call wild types, just like there are wild Pokemon. And these are the objects that our classifiers are not confident about. What that means is that there is scope for you people to tell us some information about these objects using your neural networks, your pattern matching, so that our algorithms can be improved. That is what citizen science is. And so the STEM modules that I mentioned that could be introduced in classrooms can take us in that direction, where you can be directly contributing to the science that happens with these big observatories. Again, with large surveys, it is important that we try to make sense of everything. We do a lot of computation, which is getting better and better, but our neural networks have evolved over a large number of years, millions of years. So it's not just in humans, but also from animals that came before us during evolution. So that's what we are looking at. And we have leaderboards, so you can compete against friendly competitions against others. So weekly leaderboards and long-term leaderboards, you can climb those. So we have more information about that. There are also badges for catching each of these. But the important thing is not just catching them, of course, right? You get to see how the light curve is, how you get to see how the images look, and understand how these variations are, and understanding those. So there are many local collaborations and computations that are possible with this. This is the QR code. If you scan this, it will take you to our website from where you can get to the game. So if you want to take a minute and try to scan it with your phone, you can do that. And I'll leave it there for a little bit. And then understanding the reason for these ambiguous sources is what we really want, and getting these badges. So you can share more information about this and understand it. And then you can contact me later if you're interested in this. So I'll leave with the summary now, that there are many types of opportunities in astronomy, right? As I mentioned, it's not just becoming an astronomer or an astronaut, so many different things. And you can use AI to improve your thinking, not just do computation. And make sure that you don't use AI to replace your thinking. That is critical. That is one critical aspect that we have. And then you can learn and teach astronomy through games. And I'll stop with that, and I'll be happy to take questions. Try to ask them in English so that everyone understands if you can, but if you don't understand English, which you should have told me before in the last 45 minutes, but it's okay to ask questions in Marathi too, and we can try to answer them as well. Thank you.
Okay, so I think I hope we and such amazing lecture, and you can see so much things are. So much advancement has been made, and finally also there is a game which you can also play. I hope there will be maximum downloads of this game today, and you will start playing it. Secondly, so let us begin with this question answer. So you can ask your question. Please raise your hand. I have my colleagues Rupesh and Mate, they will bring the mic to you. Yes, please.
Sir, earlier you were talking about using technology for astronomy. So, how do astronomers plan to use quantum computers in their advantages?
Okay, so quantum computers are not fully developed yet, and once they are developed, there will be ways of using those. So, that for instance, the classification that I mentioned, it can be speeded up by quantum computers a lot, but that is still a little bit way out there. It's quantum computer scientists who are still developing those, and we don't have enough qubits to do various things. We don't understand how to decipher what the quantum computer has found yet, etc. So, it will be some time before that happens.
Thank you, sir.
So, there's a question there.
So you said that the SpaceX satellites were released so that they can come together in space, but why? What's the motive?
So, sorry, what can come together?
So the two satellites that were
Okay,
released.
right. So that is in order to be able to do maneuvering in space, because later on when we want to build our own space station and we want to be able to dock a launch rocket that has been launched later on onto the space station or launch it from there, then we need to be able to maneuver them correctly so they can go. Just like I mentioned for the asteroid, it took a long time for the speed to be matched and then be able to slowly land there. That includes a lot of maneuvering. And for space stations, being able to do experiments in space, that will be required for us. Right now, we rely on other countries, but being able to do that indigenously is important.
So my question is that is ChatGPT good for the future? Because as we know that there are so many disadvantages of ChatGPT. Like if we see that some people are saying that the ChatGPT will kill the jobs of coders, because if you type anything in ChatGPT, so you will get the code. So we should become a coder or not because of the ChatGPT?
Right, that's a very good question. With most technologies, that question always comes up, is this technology good or bad for us? Because any technology in principle can be used for bad. So we saw that there were nuclear bombs that were used, but also we can use nuclear energy to energize the planet. So with ChatGPT also, that is the question, because it's a recent technology that comes up. So there are advantages of ChatGPT and there are disadvantages. So what one has to ask is that, are the advantages more or are the disadvantages more? And not just today, but 10 years from now, 50 years from now, 100 years from now. What ChatGPT has done is it has put at the fingertips of anyone detailed information about many things, which is a good thing. But it also has put detailed information about bad things at the hands of everyone. So people duping others or taking advantage of others, that is going to increase, and we have to be wary of that. And that again goes about thinking. So if you get a call from a random person claiming to be someone, how do you know whether it's the same person and so on, right? Because there are newer techniques that are being used by people using ChatGPT. So that is disadvantageous. But as a tool itself, the tool is neutral, right? It depends on us. It depends on the goodness of humans. If you are good, if you try to ensure that others are good, then it's likely to be good. And as far as jobs being lost, yes, they are going to be lost. And for any individual person who loses their job, that is a really bad thing, right? So, but if you look at in the long term, for instance, when the printing press came about, many jobs were lost. Or when the calculator was came up, we thought that okay, that's going to be bad. Or when the computers came, that was thought to be bad. So there's going to be a transition period when things are going to be bad for many people, and we should find ways to support them. For instance, one way would be to be taxing these companies which are making a lot of money, and that tax money be used for people who are being displaced, not to just distribute money to them like some political parties have been doing, but in a way so that they can be educated to learn what are the things that they should be learning in this changing environment, right? And so even for coding, just 5 years back, we used to tell our students, learn coding. That's the most important thing that you will do. And today what we are telling, oh, don't learn coding. ChatGPT does that, right? So yes, that's very important. So what we need to be teaching our students is versatility. How should they be dynamic? How should they be dynamic in this situation? So teaching coding is not the important part, but what is behind the coding? The code that you get back from ChatGPT, they're not all fantastic. You need to check the code yourself also, and it will get better. So it will get better and better code. But I guess there are people working on that. So understanding how you should be changing, understanding how you should be thinking, because if you can think better, then you can outpace these things. Because our evolution has been for a long time. And one day these computers may overtake us, but I don't think that's necessarily a bad thing, right? It should open up various good things for ourselves. But a good question, important question.
Thank you.
As we can see, war is on the horizon, and there are a whole lot of battles going on over different kinds of topics. So, do you think aerial combat will reach space?
I think it's already there in some way. So there are some satellites that are being used to do various things. So the spying is a way of combat. And also there are some countries that can do maneuvering already in space. So that's something that's going to be there. And there's a lot of, so for instance, in principle there could be, when drones are launched, right, from Earth itself, which do not reach space but just higher atmosphere and come down, that is related to that. So all those kinds of things are happening and likely to happen. And again, it is up to us, up to humanity, to try to make sure that all humans are alike each other. Look at our DNA, right? It's essentially the same. So the visual differences that you see between different people are not real differences. If we can understand that, if we can think deeply about that and become, the entire earth becomes one nation, that's the aim that we should have really.
So, excuse me. Yeah. It's a really funny question to ask, but I've seen people online buying stars from space and naming after their loved ones or something. Is that true or?
No, so NASA doesn't do that, and there may be companies that claim to do that, but you don't have star naming thing. So if you look at the older names of stars, they come after, say, Greek pantheon, or Hindus had Hindu names on that and so on. So those were old systems and they exist, but normally what is done is that constellations have alpha, beta, gamma, that is how the typical naming is. And yeah, I mean, people can pay money to get named anything, whatever they want to do. So star naming, it's not the official bodies that are naming that.
Thank you, sir.
Or I'm not taking away your money. So if someone is trying to take your money, then that's certainly not legitimate.
Sir, as you have said that you have done your PhD at IUCAA, so how can one build a career in astronomy?
Right. So some of the things that I mentioned earlier, right, that become important here. So when you're trying to do a career in astronomy, you ask yourself, what are your interests in astronomy? Is it observational astronomy? Is it computational astronomy? Is it theoretical astrophysics? And then you can build upon that. For most parts of astronomy, if you want to be in the research, there are two important things. You need to build a good base in mathematics and in physics. And in mathematics, again, statistics goes hand in hand, because with large data, that is becoming increasingly important. So get your basics of mathematics and physics right. And if you do that, then the rest can happen by its own.
Okay, we'll take one last question.
So beforehand, you mentioned the black body experiment. I'd like to know how that is relevant in astronomy and how it's used.
Sorry, what? I missed the first part of the question.
Before you mentioned the black body experiment, I'd like to know how it's used in astronomy and its relevance.
Okay, so what happens, not the black body experiment necessarily as you do in physics, but what I was showing is that the electromagnetic radiation that you have when you want to measure temperatures of different stars, the brightness that you get from that, it corresponds to a black body. So you can determine the temperatures of that using black body radiation. That is the best, closest approximation that you can do. So that's how we typically use it. Sure, and I just wanted to show how the app is used, because one other advantage of the app is when you start the app, it is based on sky map. So when you move it around in the sky, the part of the sky that you see is exactly the sky that you see. So if you want to identify, say, planets or other bodies that are out there, you can also do with that. So that's another advantage. So just as I move it around, I see exactly the sky that is behind the phone once it's adjusted. Yeah.
Let us thank him for this wonderful talk.